All right, so ready to dive into some physics.
Yeah, let's get right to it.
I was thinking, like back in the classroom, but no tests or anything, just, like the cool stuff about physics,
Absolutely.
forces and motion, energy, like what makes the world actually work?
The fundamental rules of how things move and interact.
Exactly. So where do we even begin with all of that?
Well, a good place to start is with scalars and vectors.
Scalars and vectors. Okay. What's the difference between those two?
You see, scalars are kind of like ingredients in a recipe. All you really need to know is the amount.
Okay, so just like how much of something.
Precisely. Whereas vectors, they're more like a treasure map.
The treasure map.
You need both the distance and the direction to find that treasure.
Ah, okay. I don't,
Take
yeah.
distance and displacement, for example.
Okay.
If you walk, let's say, 10 steps forward and then 10 steps back, you've covered a total distance of 20 steps.
Right, because you walked 20 steps.
But your displacement is 0.
0. But I walked 20 steps.
Because you end up right back where you started.
Oh, okay.
Distance is a scalar, only the total amount matters. But displacement is a vector. It takes into account your final position relative to where you began.
That's a good way to put it.
Yeah.
What about some other examples?
Well, speed and velocity are another pair.
Okay.
Speed is a scalar. It just tells you how fast you're going.
Like 60 miles per hour.
But velocity, that's a vector. It's 60 miles an hour, but in a specific direction.
Oh, so it has that direction part, like north or south.
Exactly. So 60 miles per hour north is a different velocity from 60 miles per hour east, even though the speeds are the same.
So vectors always have that extra layer of direction. That makes sense. Can we, add vectors together? How does that work?
We can, but it's not as simple as just adding the numbers because of those directions.
Right, because they're going in different directions.
Let's say you and a friend are pushing a heavy box.
All right, pushing a box.
You're pushing to the right with a force of 5 newtons, and your friend is pushing upwards with a force of 12 newtons.
Okay, so we got forces going in different directions.
Now, to find the total force acting on that box, we need to add these vectors together.
So how do we do that if we can't just add 5 plus 12?
Well, when the vectors are perpendicular, like they are in this case, we can use something called the Pythagorean theorem.
Pythagorean theorem.
It's from math, but it's a really helpful tool to find the combined effect of forces when they act at right angles.
Oh, yeah, I vaguely remember that. Something about triangles, right?
Yes. Imagine the forces you and your friend are applying as two sides of a right triangle.
Okay, I can picture that.
The total force on the box would be represented by the hypotenuse of that triangle.
Oh, okay, so we're using the triangle to figure out the forces.
Using the Pythagorean theorem, we can calculate that the total force is 13 newtons.
So the box is feeling a force of 13 newtons, but in what direction?
That's where we use a bit of trigonometry.
Trigonometry.
By using something called the arctangent function, we can find that the force is acting at an angle of about, let's see, 22.6 degrees from the horizontal.
So it's like we're combining physics and math to really understand how these forces are working together.
Exactly. Now, what if the forces weren't at right angles? What if they were at different angles?
Right, because not everything is perfectly at a right angle.
That's where we would use scale drawing.
Scale drawing, like we draw it out.
Exactly. Imagine a ship sailing 30 meters at a bearing of 60 degrees, then turning and sailing 20 meters east.
Okay, I'm picturing the ship.
To find the total displacement of the ship, we use a scale drawing.
So we draw out the ship's journey on paper, but make sure everything's to scale.
Yes. Using a ruler and a protractor, we carefully draw the ship's path.
Okay, so we're measuring everything out.
And by measuring the length and the angle of that final line, we can determine the ship's total displacement.
So it's like a visual way to solve these vector problems.
It is. And sometimes we need to do the opposite of adding vectors. We need to resolve them.
Resolve them. What does that mean?
It means breaking a single vector down into its horizontal and vertical components.
Oh, so we're kind of like taking it apart.
Exactly. This can make analyzing complex situations a lot simpler.
So this whole idea of adding and resolving vectors, it's got to be super important,
Right.
like, especially in real-world stuff.
Oh, absolutely.
Like what kind of real-world stuff?
Well, think about designing a bridge, for example.
Okay, a bridge.
Engineers need to figure out all those forces acting in different directions, from the weight of the bridge itself and all the traffic going over it.
Oh, so they need to make sure the bridge can handle all those forces.
They use vector addition and resolution to make sure the bridge is stable and can withstand all those forces.
Wow, so vectors are really important for keeping bridges from falling down. Okay, so we've got scalars and vectors down. What's next in our physics journey?
Let's move on to moments. You can think of a moment like using a wrench to loosen a bolt.
Okay, a wrench and a bolt. Got it.
The further away from the bolt you apply force on that wrench, the easier it becomes to turn it.
Ah, it's all about leverage.
Exactly. And that turning power, that's what we call a moment.
So a longer wrench handle means more turning power, more moment.
Precisely. And we calculate it by multiplying the force by the perpendicular distance from the force's line of action to the pivot point.
That's the point where the wrench turns, right?
Exactly.
Okay, I'm following. But what about those times when you need to turn something really tight and one person isn't enough? Like, what do you do then?
Well, then we use what's called a couple.
Couple, what's that?
A couple is a pair of forces that are equal in magnitude, but acting in opposite directions. Think of turning a steering wheel.
Oh, okay.
You're applying a couple with your hands.
So it's like teamwork, but for turning, how do we calculate the moment of a couple?
Simple. It's one of the forces multiplied by the perpendicular distance between their lines of action. Now, to understand how objects stay balanced, we use the principle of moments.
Principle of moments. All right, lay it on me.
This principle states that for an object to be in equilibrium, to be balanced, the sum of the clockwise moments about a point must be equal to the sum of the anti-clockwise moments.
So it's like a seesaw. If you have two people of different weights, the heavier person has to sit closer to the middle to balance.
Right. That's a perfect analogy.
That all makes sense now.
The principle of moments explains why seesaws work, why doors open smoothly, and why bridges can handle such heavy loads. It's all about finding that perfect balance point where the moments on each side cancel each other out.
Physics is like a secret code to understanding how everything works. So what other mysteries of physics are we going to uncover?
Next, let's explore how objects move along a straight line. We'll look at how speed, velocity, and acceleration are all connected.
All right, let's hit the gas and accelerate into some more physics.
Okay, so we've been talking about objects at rest, or moving at a constant velocity. But what about when things speed up or slow down?
Yeah, like when things change speed.
Exactly, and that's where acceleration comes in.
Acceleration, so that's all about like hitting the gas pedal and going faster.
That's one way to think about it. But acceleration is really about any change in velocity. And remember, velocity includes both speed and direction.
Oh, right, velocity is speed with direction.
So even if you're driving at a steady speed, but you're going around a curve, you're actually still accelerating.
Really?
Oh.
Because you're changing direction.
Exactly. Acceleration is any change in velocity, whether it's speeding up, slowing down, or even just changing direction.
So even slowing down is considered acceleration.
That's right. We call that deceleration or negative acceleration.
Okay, so it's all about changes in motion.
Exactly. Now, to help visualize all this, graphs can be super helpful.
Graphs, okay, like the ones with lines and axes and stuff.
Yes. For example, a displacement time graph shows how an object's position changes over time.
Okay, so like if I walk forward 10 steps, then back 5 steps, we could plot that on a graph.
Exactly. And the slope of the line on that graph actually represents the object's velocity.
So a steeper line means it's moving faster.
That's right. And a flat line means it's at rest.
Ah, that makes sense.
Yeah.
What about other types of graphs?
Well, a velocity time graph shows how an object's speed changes over time.
So we could see how fast a car is accelerating on a graph.
Exactly. The slope of the line on a velocity time graph represents the object's acceleration.
So a steeper line means faster acceleration.
You got it. And a flat line means constant velocity.
Okay, that makes sense.
And then there's the acceleration time graph, which shows how an object's acceleration changes over time.
So it's like we have all these different graphs to track motion. But what if we want to calculate specific numbers, like how far something travels or how long it takes to get somewhere?
That's where those formulas come in, those handy equations we mentioned earlier.
Oh, right, the formulas.
When an object's experiencing uniform acceleration, which means its acceleration is constant, we can use those formulas.
Okay, so uniform acceleration means the acceleration stays the same.
Exactly. Think about a skydiver jumping out of a plane.
Oh, okay.
For much of their descent, they're experiencing relatively constant acceleration due to gravity.
Until they reach terminal velocity. Right?
Yeah, exactly.
Okay, so uniform acceleration. Got it. What about those formulas? Can we see an example?
Sure. Let's say a stone is dropped from a bridge that's 50 meters high. We know its initial velocity is 0, and the acceleration is due to gravity, about 9.81 meters per second squared.
Okay, so we know all the starting information.
Using one of the formulas, we can figure out how long it takes for that stone to hit the water.
We can actually calculate that just from knowing a few things. It's pretty cool.
It is. Now let's switch gears a bit and talk about projectile motion.
Projectile motion. Sounds fancy.
Think about throwing a baseball, shooting a basketball, or even launching a rocket.
Okay, so things moving through the air.
Exactly. And what makes projectile motion interesting is that it happens in two dimensions, both horizontally and vertically.
So it's not just moving in a straight line anymore.
Right. And what's really cool is that the horizontal and vertical parts of the motion are independent of each other.
Wait, what does that mean, independent?
Imagine you're on a train that's moving, and you toss a ball straight up in the air.
Okay, tossing a ball on a train.
Whether the train's stopped or moving at a constant speed, the ball will go straight up and come straight back down to your hand.
So the ball doesn't move sideways with the train.
Right. The ball's vertical motion isn't affected by the train's horizontal motion.
Wow, that's weird to think about. So we can separate the horizontal and vertical motion.
Exactly. And speaking of gravity, let's talk about free fall.
Free fall. Isn't that like falling without any air resistance?
Well, technically, yes. But here on Earth, we have air, which creates resistance.
Right, so things don't fall perfectly straight down.
But for a brief time, before air resistance has a big effect, objects do experience something very close to true free fall.
So it's all about gravity being the main force acting on the object.
Exactly. And speaking of forces, that brings us to friction.
Friction. That's like when things rub against each other and slow down, right?
That's right. Friction is a force that opposes motion. It happens when two surfaces rub together.
Like when I try to slide a book across a table.
Exactly. And friction can convert kinetic energy, the energy of motion, into other forms of energy, like heat or sound.
So that's why my hands get warm when I rub them together.
Yeah,
Friction making heat.
precisely. Friction is all around us, and it plays a key role in how things move.
Wow, friction is way more interesting than I thought. Okay, so we've got free fall, friction. What other forces are there?
Well, there's lift. That's the force that allows things like airplanes to fly.
So it's like an upward force.
That's right. And all these forces are governed by a very important set of rules, Newton's laws of motion.
Newton's laws, aren't those like the fundamental rules of physics?
They are. Newton's first law of motion tells us that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by a net force.
So things just want to keep doing what they're doing unless something forces them to change.
Precisely. It's all about inertia, an object's tendency to resist changes in its motion.
Okay, so that's the first law. What about the second?
Newton's second law gives us a mathematical relationship between force, mass, and acceleration.
So it's like an equation.
It states that the acceleration of an object is directly proportional to the net force acting upon it, and inversely proportional to its mass.
Okay, so the more force, the more acceleration, but the more mass, the less acceleration.
Exactly.
Makes sense. What about the third law?
Newton's third law of motion states that for every action, there is an equal and opposite reaction.
Oh yeah, I've heard that one. So if I push on a wall, the wall pushes back on me.
You got it. Forces always come in pairs.
Oh, wow, Newton really figured out how forces work. It's amazing how these laws apply to everything around us. What other cool concepts are waiting for us in the world of physics?
You know those laws Newton came up with? They really set the stage for understanding so much about physics. Now, let's talk about momentum. Think of it as, well, a measure of an object's mass in motion.
Okay, so like a big truck going fast has a lot of momentum.
Exactly. A heavy object moving quickly has a lot of momentum. And there's a really important principle called the conservation of momentum.
Conservation of momentum, what's that?
Basically, it means, though, in a closed system where nothing's coming in or going out, the total momentum before something happens, like a collision, has to be the same as the total momentum afterwards.
So the momentum can move from one object to another, but the total amount always stays the same.
You got it. It's like a cosmic balancing act for motion. Think about two billiard balls colliding.
Okay, like on a pool table.
The cue ball smacks into another ball, and some of its momentum gets transferred.
Right, so the other ball starts moving.
But the total momentum of the whole system, it stays the same.
Interesting. But what about car crashes? Like, the momentum seems to just disappear when the cars crumple up.
Ugh, that's a good question. In a car crash, the momentum doesn't just vanish. It gets transferred to other things, like the road or the air.
Oh, okay.
And some of it's converted into other forms of energy, like heat and sound, as those cars deform. That's why crumple zones are so important in car design.
Crumple zones. So they help absorb some of that energy.
Exactly. They help reduce the impact on the people inside the car. Now, another concept that's tied to momentum is impulse.
Impulse.
It's the change in an object's momentum. It's equal to the force you apply multiplied by the time that force is acting.
So if you hit a golf ball with a club, that's a big force for a short time, which makes a big change in momentum.
Precisely. But if you gently push a swing, it's a smaller force over a longer time, and it creates a smaller change in momentum.
Makes sense.
And this idea of impulse, it helps us design safer things like helmets or car airbags.
Oh, so understanding physics helps us make things safer.
Absolutely. Now, are you ready to tackle work, energy, and power?
Bring it on. I'm starting to feel like a physics pro.
Well, work is done when a force causes an object to move. Think about lifting a heavy box.
Okay, I'm picturing it.
You're applying force upwards, and that box is moving upwards. That's work.
So lifting weights at the gym is definitely work.
It is. And energy is closely related to work. Energy is basically the ability to do work.
Okay, so it's like the fuel for doing work.
Exactly. There are different kinds of energy, like kinetic energy, which is the energy of motion, and potential energy, which is stored energy.
So a rolling bowling ball has kinetic energy.
Yes. And a book sitting on a shelf has potential energy because of its position.
Got it. What about power?
Power is how quickly work is done or how fast energy is transferred.
So a more powerful engine can do the same amount of work faster.
Exactly. It can generate and use energy more quickly. Now, one of the most important ideas in physics is the conservation of energy.
We talked about conservation of momentum earlier, right?
Right. This one means energy can't be created or destroyed, only transformed from one form to another.
So it's like energy is always changing, but the total amount stays the same.
You got it. Think about that pendulum swinging back and forth. It's constantly switching between kinetic and potential energy, but the total energy remains constant.
Physics is full of these amazing patterns.
It is. Now, shifting gears a bit, let's talk about the bulk properties of solids.
Bulk properties, like
Yeah.
what solids are made of and how they behave.
That's it. One important property is density.
Oh yeah, density, like how tightly packed something is.
Exactly. A dense material, like lead, feels heavy for its size because its atoms are packed closely together.
Makes sense. What other properties are there?
Well, there's Hooke's law, which describes how materials stretch or compress. Think about a spring.
Okay, a spring.
Hooke's law says that the force needed to stretch or compress that spring is proportional to how much you stretch or compress it, but only up to a certain point.
So if you pull a spring twice as hard, it'll stretch twice as far.
Exactly, but there's a limit called the elastic limit. If you stretch it too far, it'll permanently change shape.
Like bending a paperclip too far, it stays bent out of shape.
Precisely. That's called plastic deformation. And this all ties back to things like crumple zones in cars, which are designed to deform in a crash to absorb energy.
Wow, it's amazing how all these physics concepts connect to real-world applications.
It is. Physics is everywhere, from the tiniest particles to the largest structures in the universe.
I've learned so much today. I feel like I have a whole new understanding of how the world works.
It's been a fantastic journey exploring the world of physics with you.
Thanks for taking us on this deep dive. It's been an incredible learning experience. And to all our listeners, keep those brains buzzing and never stop exploring the wonders of physics.